this will work. Right, thank you very much. It's a pleasure to be here. It's a great honor to be able to speak at this conference. I'm going to talk about some work that I've been doing in collaboration with Neil Turok and his student Joop Veldbrugge, and also with my student Alice Ditucci. And it's about a very similar setting than the one Thomas has just been talking about, namely the beginning of space and time. Now, there's an old idea, dating back to Lemaitre, that the universe could have had a quantum origin. And in fact, there seems to be nothing that prevents this from happening. You know, the idea is that a closed universe would have all total charges zero, and there seems to be no obstruction to a universe just coming out of nothing. Now, the most precise formulation of this statement, or a more precise formulation of this statement, came with Stephen Hawking, where he said that, you know, the boundary condition of the universe should be something very special, and what could be more special than having no boundary? And there's a very closely related proposal due to Vilenkin, in which he pictures the emergence of the universe as a kind of a smooth tunneling phenomenon. Right? In both cases, the idea is to replace the Big Bang singularity by something non-singular, something smooth, and in fact, you know, in classical general relativity, this is not possible, but with semi-classical geometries, one could hope that this can be done. The question is, however, how do we calculate this? You know, how do we make this precise? From the outset, the idea was that this should be done in the path integral formulation of gravity, and that one should be able to describe these processes by saddle points of the integral. But saddle points of which integral? Now, the first approach has been to try this in Euclidean quantum gravity, where it was hoped that, in analogy with the standard Wick rotation in quantum field theory, that doing a summing over Euclidean spacetimes would lead to better convergence properties of the integral. Now, whether this actually works is not so clear because of the conformal mode problem. So if you have an action containing gravity, then the part of that describes the scale factor of the universe, here denoted by little a in the action which I'm writing down, the kinetic term for this scale factor little a has the opposite sign than the kinetic term of any other matter fields, here denoted by phi. And because of this difference in sign, you know, it's not clear that, well, and in fact, this implies that the action is not bounded, neither above nor below. So it is not at all clear that an approach based on the Euclidean path integral can lead to a convergent result. On the other hand, the Lorentzian approach, in which you sum over e to the is, you're just summing over phases, so it doesn't particularly matter that you have the conformal mode problem, but you have a very highly oscillating integral, and you're not sure whether it in fact converges at all or not. So here what we're really interested in will be the Lorentzian path integral. Now, in a simple mini superspace context with a metric just given in the third line there by minus n squared dt squared plus a squared d omega 3 squared, here little a, as before, denotes the scale factor of the universe. N is the lapse function which determines the total time evolution. We're choosing a time coordinate which runs between fixed values, say between 0 and 1, and then capital N, the lapse function, will determine the total time of evolution, the proper time. The omega 3 squared is just the metric on a round 3 sphere here. Now, the path integral then will be an integration over this lapse function n and the scale factor a of the universe. And we're taking as our action just the action for gravity coupled to a cosmological constant for simplicity. But many of the results that I will show actually extend to the case where you have a scalar field in the potential, for instance, if you have an inflationary context. Now, the action that you get from this metric is still complicated to handle. It's given in the bottom line here. But there exists a coordinate system, a field redefinition, due to Halliwell and Luco, which makes the action much more tractable. So you redefine the scale factor squared of the universe as q, and you change your time coordinate to be given by, in the metric by minus n squared over q dt squared. So this t coordinate parameterizes time, but it's not the standard time. And in fact, it has no special physical meaning, but it makes the mathematics much simpler, because it results in an action which is actually quadratic in q. Now, this means that one can just do the integral over q exactly. So the fact that the action is quadratic means that the equations of motion for q can be solved. One can then do the integral by changing variables of integration to a solution plus a random fluctuation. And again, because the action is quadratic, that random fluctuation will just give rise to a Gaussian integral, which can be done. So what we end up with is an integral simply over the lapse function, simply over the total time between our original and final configuration. This is simply an ordinary integral, but it's a complicated integral to do. So it's an integral, as I said, over the lapse function, e to the 2 pi squared I S0, where S0 is now the effective action in terms of the lapse, which contains a term in n cubed, n, and 1 over n. This integral cannot be done exactly. But a question is already whether this is an integral that actually converges or not. It's a Lorentzian integral, it's highly oscillating, and it's not clear a priori that it has any meaning at all. In fact, if we use a canonical variable, capital M here, which is just the square root of n, then we see that the asymptotic behavior of this integral at large m will go like e to the I m to the 6, and at very small m will go like e to the I over m squared. Okay, so the question is now, at small n and at large n, does this integral actually converge? Now, there's a simple criterion for alternating series, which is the Leibniz convergence test. If you have a series, here, sum over minus 1 to the I ai, an alternating series, then this series will converge if the terms become successively smaller and if they limit to 0. Now, one can quite easily construct such an alternating series or re-express the integral which we have as an alternating series. So we have an integral that we're interested, which is of the form integral over dx e to the I x to the n, where we're interested in the special cases where little n is equal to 6 or minus 2. The argument which I will give presently works for n greater than 1 or n smaller than minus 1, so it works in both cases. Now let's just take the real part of this integral, and the same will work for the imaginary part. So it becomes just an integral over cosine x to the n. You can actually easily see just from plotting the integral that this will satisfy the Leibniz convergence criterion, because the oscillations get faster and faster, and you can divide up the integral by just integrating over the portion above the real line and below the real line. So in this way, you get an alternating series, and as you can see from the graph already, each successive contribution gets smaller in magnitude than the previous one, and it will tend to 0. So this integral satisfies the Leibniz convergence test, and this means that this integral, this highly oscillating integral, actually converges. The question is, of course, then, what does it converge to? Now, we just have a criterion here which shows that it does converge, but doesn't give us any easy way of really evaluating it, of obtaining a numerical result. This can be done by using what's known as Picard-Lefschetz theory, which is a mathematical framework which is precisely designed to deal with oscillating integrals. The idea is that we start with an oscillating integral, like the standard Feynman path integral, but now we extend it to the complex plane. So we view the fields as holomorphic functions, and they're extended to the complex plane. And the idea is then that by deforming the contour of integration, we can find a nicer contour on which we can evaluate this integral. So note that this is different from Wick rotation, where you just analytically continue the time coordinate. Here we're analytically continuing the fields, which in the context of relativity seems much more appropriate. Now, So we know from Cauchy's theorem that, of course, we can deform any contour of integration in the complex plane at will, as long as we're not crossing any singularities. But Cauchy's theorem doesn't tell us how we should do it. We're free to do it in an infinite number of ways. You can think of Picard-Lefschetz theory as just giving you the optimal way of deforming the contour of integration. So let me just show you graphically what we're trying to do. Say we start with an integral defined on this orange contour C on the bottom left. And say this is a highly oscillating integral, like the one we're interested in. So at the bottom right would show this integral with many cancellations. Now there might be a path, in fact a path of steepest descent, along which this integral is not oscillating at all, but is converging as fast as possible. This is shown in the top right by the green path. And you see, of course, if there is such a path, it will originate from a critical point of the action, a critical point sigma here. And in fact, in this context, the critical point is always a saddle point of the action. So the idea is that we will deform this orange contour, C, to a different contour here called J sigma, along which the integral converges. But we're not changing the integral. We're just deforming the contour. We're not changing the endpoints of integration. This contour of steepest descent is also called a Lefschetz thimble. Now, an important point is that because we're starting with an integral which has many cancellations, and we want to replace it with something which does not have cancellations, this means we have to flow down in the magnitude of the integral. And that means that this path, this steepest descent path, J sigma, this Lefschetz thimble, will only be relevant to the integral if it lies lower than the original contour. If there is another such thimble, if there are other critical points, but they lie higher up than the original, contour of integration, then they will not be relevant. You can say this a bit more formally, that we want to write our original contour of integration C as a sum over such Lefschetz thimbles with coefficients n sigma, and these n sigmas will only be non-zero if one can flow down towards these critical points. This means that one can rewrite the original highly oscillating and only conditionally convergent integral as a sum over manifestly or absolutely convergent integrals along these Lefschetz thimbles. Let me give you a brief example. There's a canonical example provided for this, which is the Airy function. The Airy function can be defined as an integral over e to the I x cubed over 3 plus phi x. And as before, this is a highly oscillating integral, and it's not clear a priori whether it will converge or not. So according to Picard-Lefschetz theory, we should look at the saddle points of this integral, which you can easily see the saddle points of the exponent are given by plus or minus I square root of phi. In this case, we have two such saddle points, and we can numerically look at the lines of steepest ascent and descent, as I've shown in this figure. So we have these two saddle points, which are at these red intersections. But the question is, do these now contribute to the integral or not? Let me show in a bit more detail what this diagram means. So we have these two saddle points, which are marked in orange. And then in black, we have the lines of steepest ascent and descent. J are the descent lines, K the ascent lines. In green, I've shown regions in which the integrand becomes smaller and smaller. So asymptotically, these will be regions of convergence. In red, the integrand gets larger and larger in magnitude, and so asymptotically, these are regions where the integral just diverges. Now, if we assume that our defining contour is along the real line, this orange line that I'm showing in the middle, the question is now, how can we deform it into a sum over Lefschetz thimbles? Now, in this case, it's very easy to flow to the we have to flow it down. So we have to follow the arrows on these black lines, which show the downwards flow. And that means that actually we have to move the contour up in this graph here. And only the saddle point in the upper half plane contributes to this integral. One can imagine other situations where you look at different arguments of the area function, then these two saddle points move around, and there can be situations where both saddle points contribute, but there can also be situations like here where only one contributes. The nice thing is that Picard-Lefschetz theory gives us a systematic way of finding out which saddle points contribute, and therefore how we can approximate our mathematical result. So let's get back to our integral over the lapse function, so the integral over the total time evolution of the universe. We want to calculate this integral now from zero size of the universe to a large final size of the universe. In this formula, I'm denoting the initial size by Q0, the final size by Q1, and we will be interested in the limit where this Q0 tends to 0, so where the universe really comes from nothing. So we should look at the saddle points of the integrand. There's 4 of them. And whether they tend to be real or end up being real or complex depends on the boundary conditions. If we look at a classical large universe, say the universe expanding from today until tomorrow, the boundary conditions will be classical, the saddle points real, and we do recover just a standard description of an expanding universe. But we're interested in the case where we let the initial size of the universe go towards 0. This corresponds to a process which classically is not allowed. It's a quantum tunneling event, and therefore the saddle points actually become complex. That's a way of saying that we're describing quantum theory and not classical theory. So one can again numerically evaluate the saddle points and the associated flow lines. Here they are. And let me show you on a graph a bit more precisely which ones are the directions of ascent and descent. So we have the 4 saddle points in orange. They're labeled 1, 2, 3, 4. And then the associated lines of steepest descent J and steepest ascent K. Again, green are regions which asymptotically converge, red they diverge, and yellow are regions which are in between saddle points. Our defining contour, because we're interested in the Lorentzian path integral, is along the real half-line from 0 to infinity. So this is, again, the orange line in the center of the graph. Now, again, we'd like to know how should we deform this contour, because along this contour, the integral is just oscillating. How should we deform it to get a nicely and absolutely convergent result? So we have to flow this contour down. We have to, again, follow the arrows, and that means that only saddle point 1, in fact, contributes. And only this Lefschetz thimble, this path of steepest descent that intersects the saddle point 1, contributes in the end. We have to make sure that the arcs near 0 and near infinity do not contribute, so that really we can apply Cauchy's theorem, that we don't get extra contributions. But it's easy to show that, in fact, these arcs in the limit where you take them towards the origin or towards infinity just yield 0 additional contribution. So we have a single saddle point that's relevant for the integral, which means we can just directly approximate the integral. And this is the resulting expression that we find. There's a prefactor, and then the main behavior is given in the exponent, e to the minus 12 pi squared over h bar lambda, and a phase factor which goes as q1 to the 3/2. q1 was the square of the scale factor of the universe, so in fact the phase goes as the volume of the universe, which is the expected behavior. The prefactor, the weighting, turns out to be not the one that Hartle and Hawking had suggested, but is the one that was suggested in Vilenkin's tunneling proposal, e to the minus 12 pi squared over h bar lambda. This minus sign, so the fact that it goes as e to the minus 1 over h bar lambda instead of e to the plus 1 over h bar lambda, is easy to understand from the point of view of Picard-Lefschetz theory. We're starting with a definition of the integral where the integral is along real fields, but we're integrating over e to the is. Now, the real part of is is then 0 in the starting integral, and Picard-Lefschetz theory says that we have to flow down to find a relevant saddle point. That means that the weighting must be negative. And so it's completely clear that we should find minus 1 over h bar lambda and not plus 1 over h bar lambda. Moreover, this has the property that as you send h bar to 0, as you make quantum mechanics less important, this effect gets suppressed and not enhanced. So far, so good. We should, of course, now see what happens to perturbations in the universe. At the moment, we've just described a completely smooth isotropic universe. But what about the perturbations? So we should add perturbations and integrate from 0 size of the universe to a final size of the universe, Q1, and a final fluctuation, phi1. For simplicity here, I will simply look at one gravitational wave mode with a particular wave number L. One could extend this to sums over arbitrary numbers of modes, but it's simpler and it's enough to just look at a single mode. In the coordinates which I was using, the action for the perturbations at quadratic order is given on the bottom of this slide. Now, because I was specializing to a pure cosmological constant, it turns out that you can just solve the mode functions for these perturbations exactly. So there are solutions. They're slightly complicated. They're given here in terms of physical time. The solution is in the middle. It depends on a linear combination of two expressions with coefficients C1 and C2. But we still have to impose the boundary conditions. Now, the no boundary condition implicitly, well, not implicitly, but the idea is, of course, that the solutions should be regular at this, when the universe is created. The whole idea is to replace the singularity of the Big Bang with something that's smooth. So we have to take a solution which is also smooth, which is not blowing up at the beginning of the universe. And this means that, in fact, this second line proportional to C2 has to be set to 0. We need to set C2 to 0. We're just left with the top line. So we have an explicit expression for the regular perturbation, and we can just calculate the action associated with this, and we can see what we obtain. One can expand the action at large values of the final universe, and one gets an expression similar to the one gets the expression, the leading term is in this box, right? And the weighting of the propagator to go from 0 size to a final size with fluctuations phi1 is given by this exponent, e to the plus phi1 squared times roughly L cubed over h squared. The L cubed just means that we have a scale invariant spectrum of fluctuations. H is the Hubble rate, the expansion rate, which is expected in this context. And phi1 is the final size. However, the crucial thing is that we find e to the plus phi1 squared. So instead of finding a standard Gaussian distribution of fluctuations, one finds an inverse Gaussian distribution. That means that these fluctuations are unstable. Larger fluctuations get a larger weighting, and so in the end, this model breaks down. Now, in some sense, you can ask what went wrong, and one way of interpreting what this calculation is saying is that really there were two possibilities of having a complex saddle point, and they correspond to doing the Wick rotation in two different directions. In one direction, we would have obtained a Gaussian saddle point. In the other direction, we get this inverse Gaussian distribution. And Hartle and Hawking had suggested that it is the Gaussian saddle point that should be the final result. However, when we define this integral precisely as a Lorentzian path integral, we see that here, just by mathematics, by Picard-Lefschetz theory, we are forced to take the wrong Wick rotation. It's not that we don't have a choice about it. We just find this unstable result. Now, you can ask whether our approximations here break down. So we have checked numerically that if we extend the metric from an isotropic metric to a Bianchi 9 metric, we can numerically evaluate, again, this just repeat the whole calculation numerically, and we find that in fact this instability gets stronger. Another point of concern, before I go to that, another implication of the result is that we can also now look at the Euclidean integral, which was the original integral that was supposed to be the object of greatest interest. Now, a Euclidean integral here would correspond to integrating along the imaginary axis of the time of the lapse function. And you see, now, it doesn't particularly matter whether you choose the upper half imaginary axis or the lower half imaginary axis. You always run into one of these red regions where the integral diverges. And so, no matter how you define it, the Euclidean integral just diverges and is mathematically meaningless, which was in a sense expected from the conformal mode problem. So this means that the Euclidean path integral in the presence of a positive cosmological constant simply doesn't exist. Now, our results have prompted Thomas, together with Jim Hartle and Jonathan Halliwell and their collaborators, to also try out other definitions of the contour for the lapse functions. These, where it's neither Lorentzian nor Euclidean, but where they propose an inherently complex contour. Now, in our view, these proposals do not currently work yet, but our discussion continues. And I think, the last word hasn't been said yet about these alternative definitions. Now, one may also ask whether the way of doing this calculation was simply wrong. That, the way of just integrating from a zero-size universe to a final-size universe was perhaps not in the spirit of the no-boundary proposal. Because when we do this, we integrate over a number of quite singular geometries. And the whole idea was to replace the Big Bang with something smooth and non-singular. For instance, when you look at the perturbative action, there are branch cuts in the plane which come from the bad behavior of the fluctuations. Moreover, really which we're summing over are not just the smooth geometries which are rounded off, but some of them have a singularity, some of them even have two singularities. That's just because gravity is attractive and likes to make singularities. So when we just do an unrestricted path integral of a gravitational matrix, we will necessarily find many singularities. We could manually excise them, and they all lie on the real n line. And there it's interesting to see that the thimbles over which we ultimately integrate are not affected by this. However, one can do better. One can also just explicitly integrate over only regular metrics. This is a calculation that also was tried first by Halliwell and Luco in the late 1980s. And we recently, my student Alice Ditucci and I, we recently extended this to include perturbations. So here the idea is that we want to restrict the integral over just purely regular metrics, essentially just different complex force spheres, so that there is no singularity anywhere. And we're finding that in this case, again, the same instability arises. The fluctuations, again, lead to an inverse Gaussian distribution. Note that for each given final fluctuation size, we get a convergent result. It's just that the physical interpretation that we get an inverse Gaussian doesn't make sense in the end. But every step of the calculation is manifestly finite. So I think the main lessons from this work are that, at least in mini-superspace, the Lorentzian integral for gravity, the Lorentzian path integral for gravity makes sense. While the Euclidean one, which was in the past considered to be the main object of interest, is simply not defined mathematically. And so in the end, I think that the quest for a theory of initial conditions is still open. Thomas presented a new way of looking at this by going much more in taking the quantum side much more seriously, and that may be the way to go. But I think in general, there is still a big question mark regarding the initial conditions for the universe. These methods which we're employing here have many applications. For instance, it's interesting to ask, here we're finding this mismatch between background and fluctuations. The background forces a particular Wick rotation, which then causes the fluctuations to be unstable. Is this always like this? Or can there be other dynamics, other matter types that actually, that circumvent this problem? And then more generally, can we use these mathematical methods to define Lorentzian path integrals in a general sense, not just in mini-superspace? Can we describe quantum bounces now using these methods? And also, we can use these methods to even test whether quantum field theory in curved space-time is typically a good approximation or not. Because here we're going beyond quantum field theory in curved space-time. The background itself is quantized. And so we can ask, for instance, at the early stages of inflation, is quantum field theory in curved space-time actually applicable? Or if not, what does it get replaced by, and what do we learn from this? Thank you for your attention.
Thank you.